In this video, we want to take the average rate of change of a function and combine it with the idea of a limit to define the instantaneous rate of change to be the limit of the average rates over shorter and shorter intervals. And the instantaneous rate of change is also known as the derivative. So here is a quick review of the definition of the average rate of change. We're going to have a function, f of x, and an interval of x values, which we're going to label as from a to a plus h. And the average rate of change from a to a plus h will be the change in y, denoted by delta y, divided by the change in x. Well, at the point a, the coordinates of that point are going to be a, f of a. And at the other end of the interval, the coordinates are a plus h and f of a plus h. So the change in y will be the difference in the two second coordinates, f of a plus h minus f of a, and the change in x will just be h. So the average rate of change is also represented geometrically by the slope of the secant line from a to a plus h. And it's important to remember that the average rate of change is always measured over an interval of x values. Now suppose we start with a function f and a single domain value a, and we want to define the instantaneous rate of change of f at a. We're going to define it as the limit of the average rates over shorter and shorter intervals. So you'll recall from the previous slide that this quotient represents the average rate of change of f from a to a plus h, and in this diagram, if we set our h value over to here, then that quotient is the slope of that secant line. And now we want to let the limit, we want to take the limit as h gets closer and closer to 0. So if we now slide h towards 0, we see that the secant lines, which give us the average rates of change, will approach a limit, and that limit will be the tangent line to f at a. So the slope of that tangent line will give us the instantaneous rate of change of f at a. Here's an example. The graph shows the volume of water after t minutes in a draining tank. First, we want to estimate the average flow over the first 30 minutes. So we need to look at the function at t equals 0 and again at t equals 30 and compute the change in volume over the change in time between those 2 points. Well, we want v of 30 minus v of 0 divided by 30 minus 0. And we're now going to use the graph to estimate the values of v. So v of 30 is approximately 22.5, and v of 0 is 40, and then delta t is 30. And now we just need to do the arithmetic. So the numerator is minus 17.5 divided by 30, which gives us about 0.58. And then I'm going to multiply by 1,000, because those are the units along the volume axis, and we get an average rate of change of minus 580 gallons per minute. And it's a negative value because the volume is decreasing. In the second part of the question, we want to estimate the rate of flow at 60 minutes. And in this case, since we don't see the word average, we're really being asked about the instantaneous rate of change, or the instantaneous rate of flow. And in this case, it's at 60 minutes. So the instantaneous rate is going to be the slope of the tangent line at 60. So I'm going to draw a tangent line segment to the graph at t equals 60, and then I'm going to use the endpoints of that segment to estimate the slope. So at the left end of that segment, the coordinates of that line are at 30, 20, and at the other end they're at 90, 0. So the slope of the tangent line is going to be approximately the difference in the y coordinates, 0 minus 20, divided by the difference in the x coordinates, 90 minus 30, which will give us a value of about minus a third. And then we're going to multiply by 1,000 to get an instantaneous rate of change of minus 333 gallons per minute. And then for the last part of the question, we want to know, when is the tank draining the fastest? Well, that's going to occur when the tangent line to the graph has the most negative slope. And this occurs at t equals 0. So if I were to draw a small tangent line segment at t equals 0, you can easily, I think, convince yourself that the slope of that tangent line will be the most negative. If we were to move to some other point on the graph, we would get a tangent line that had a smaller negative slope. We now want to take the instantaneous rate of change and give it its calculus name. So we're going to define the derivative of f at a and denote it by f prime of a to be the rate of change of f at a, which geometrically will be the slope of the tangent line to f at a, and we'll find it by taking the limit of the average rates of change over shorter and shorter intervals. In this example, we want to take the function 2 over x and find the equation of its tangent line at the point 2, 1. Well, let's start by observing that in order to find the equation of any line, we need the slope. And now we know that the slope of the tangent line will be the derivative, f prime, at the value 2. And now using the definition, f prime of 2 will be the limit as h goes to 0 of f of 2 plus h minus f of 2 over h. So we're using the definition of the derivative with a equal to 2. And now we need to evaluate this limit for the function 2 over x. Now f of 2 plus h will be 2 over 2 plus h. F of 2 is 1, and then we have a divide by h. And in order to evaluate this limit, we're going to do some algebraic simplification. So let's start by getting a common denominator in the numerator here. So we'll have 1 changed to 2 plus h over 2 plus h. And now we can combine the terms in the numerator. And then simplify. 2 minus 2 plus h will look like this. And then I'm going to rewrite the expression as a multiplication problem. Then we can cancel the h's, simplifying this to minus 1 over 2 plus h, and now I can take the limit and I find that its value is minus a half. So that's the slope of the tangent line. Now to get the equation of the tangent line, we'll use the point slope formula. So we'll have y equals, the slope is minus a half, and then we'll fill in the x value, x which is 2, and the y value, which is 1. And then here's a picture of 2 over x and the tangent line. In this next example, we want to highlight the difference between a function f and its derivative f prime. So suppose you have a function f of t, which represents the number of bacteria after t hours growing in a laboratory dish. What does f5 mean, and what are its units? Well, f5 would represent the population size, or the number of bacteria, after 5 hours, and its units would simply be the number of bacteria. f prime of 5 represents the rate of change, or rate of growth, in the population after 5 hours. Its units would be the number of bacteria per hour. And the third question says, if we have no limits on space or nutrients, which is bigger, the rate of growth after 5 hours or the rate of growth after 10 hours? Well, we would expect f prime of 10 to be greater than f prime of 5. The bacteria population should be growing faster after 10 hours than it is after 5 hours, because there will be more bacteria to reproduce after 10 hours. suppose we drop a ball from the top of a 490-meter tower. The distance it has fallen after t seconds would be given by the function 4.9 t squared. How fast is it going when it hits the ground? Well, the first thing that we need to do is determine when it hits the ground. And for that, we'll set the value of the function equal to 490 and solve for t. So we'll have t squared is 490 divided by 4.9, which is 100. And then taking the square root, the ball will hit the ground when t is equal to 10, or after 10 seconds. So now, to find out how fast it's going, we need to calculate the rate of change, or the derivative, at 10. So the velocity will be s prime of 10. And to calculate s prime of 10, we'll start by writing down the definition. And now we need to evaluate this limit for the function 4.9 t squared. So let's start out by writing s of 10 plus h minus s of 10, which is 4.9 times 10 squared, divided by h. And now we need to do some algebra to calculate this limit. We'll begin by expanding out the 10 plus h squared. And then simplifying the s of 10, and then we still have our h in the denominator. Now we want to multiply the 4.9 through the parentheses. And then we still have the rest of the expression. Now we can cancel the 490s and simplify. And what we've done is to factor the h in the numerator. And then we'll cancel the h in the numerator and the denominator. And finally we'll be able to take the limit as h goes to 0, and we'll find that the velocity after 10 seconds is 98 meters per second. Here's a summary of the ideas in this video.